Team recording. Okay, so I hope everybody is doing well. So let's get started with the content for today. Okay, so last time we were talking about, we were basically recapping and motivating the, what are the different parts of this course and, how they may be similar and dissimilar to what you've seen in some of the previous courses. What is the overall picture? And then we picked up a couple of things which were new. One is, of course, the revision of a typical classification pipeline. And then we started looking at chain rule, what is also called back propagation. Okay. And towards the end, it was a little bit rushed, and so I'm going to kind of start from there. Was how the model that we introduced through the lecture last time, which was actually a linear model, something like Wx plus b. It's not even, it doesn't work well even with a two-dimensional data set. Okay, and that's a very specific toy two-dimensional data set, but it will give you a gist of why you would like to have richer models, and in particular neural networks. Okay. So before I get into the content, just to recap, what we did not cover last time is what we covered but did not, we're going to retouch it or revisit them today, is how chain rule works. In particular, for example, how PyTorch and TensorFlow behind the scenes do something similar to what we'll look at. And then we'll look at why multi-class logistic regression, which is the model that we saw last time, doesn't work that well. And then today's content is about introducing two most popular, I would say, are the starting points within the class of neural network architectures or deep neural network architectures. The first one is called a feedforward neural network. And mostly there we'll try to understand what I call hidden, mostly understand the terminology used when discussing neural network architectures, what I call hidden layers and what are non-linearities and so on. We'll also use the example from before, so this multi-class logistic regression, and show how we can improve on that if we use a feedforward neural network. The second part of this lecture will look at convolutional neural networks. So these are a slightly different, they have a slightly different architecture, and by which, so I'm using the word architecture again and again. We'll discuss what it means to have that word and what it means for a model to have, an architecture. So convolutional layer will be an important component of that model. So we'll understand what a convolutional layer is, and along with that, how a few additional layers complete the definition of the model, of a convolutional neural network model. Okay, so that's the goal for today. So without ado, we'll actually look at some of these links during the session. So let me actually get started with where we were last time. Can everybody see my screen with backdrop?
Yes.
Okay. Okay. So good. So I'm gonna spend a little bit more time. Hopefully, folks had some time to revisit these slides as well as the recording from last time. So backdrop is an important tool to accomplish that optimization step that we discussed while we were reviewing classification pipeline. Remember, there was a model aspect, there's a data aspect, there's a objective, which is the model, what is considered the best model, and then the actual getting to the best model, which is through optimization. And we said we are going to use what are called gradient descent techniques. Okay, so gradient, if you remember, is just the gradient of a function is with respect to its input is just the partial derivative with respect to each of its inputs. So that's the gradient. Okay. So what we want to do when we try to search for the best model is we want to get a gradient of the loss with respect to the parameters of the model. Okay. So that's what we want to use in machine learning. So whether it's a deep learning model, whether it's some other model like even an SVM model or a logistic regression model, we can always define a loss, right? So for each of these models, whatever loss we're trying to minimize. And ideally, if we had access to the gradient of the loss with respect to the parameters of the model, whether they are linear parameters, SVM's parameters, logistic regressions parameters, or deep learning models parameters. As long as you can get the gradient, we can start with some initial parameter set, parameter values, and use the gradient update rule to get to a new parameter values, set of parameter values, and then keep on improving, keep on iterating like that. And there was a graphic I think we showed last time where there's a valley. Ideally, hopefully, for example, for multi-class logistic regression, there is the loss function looks like a U or a parabola, and so you can get to the bottom of the valley if you do this gradient updates. Okay, so that was the overall picture, but let's actually pick up a specific detail, which is how do we get this gradient? Okay, so we can't always hand derive, use pen and paper to figure out, hey, what is the gradient of the loss with respect to parameters? Okay. So computers do it automatically, and the way they do it is using chain rule. Okay, variations of chain rule. So let's understand chain rule or backpropagation. Okay, which is the idea that if you want to get so in this figure, what I'm trying to show is a node. Okay, so this is a graph. So in a graph, there's what are called nodes, which connect edges. Okay, so think of these blue lines as edges, and this huge circle as one node in a big graph. I mean, we are ignoring the graph. We are only focusing on the node here. Okay. Let me check the chat because I missed the chat. Okay. Okay, so we're only focusing on the node. And the idea with chain rule backpropagation is that you don't have to worry about how the whole graph looks like. You as in the, there is going to be some repetitive computation. So there's going to be some computation at each node of this graph. Okay, and that's why we'll call it a computational graph. You'll see in the next slide. And each node doesn't have to worry about what else is there in that graph. Okay, so maybe I'm a node which is computing given two inputs A and B. I'm producing an output which is h of A comma B. Think of h of A comma B as like A times B, for example, a simple multiplication operation. Okay, that's what this node's job is. This node doesn't need to know later on, hey, A is going to get transformed by A square or something like that. You don't need to know that. Okay, but this node, what it can do is locally compute its gradient. Okay, which is that it can compute how does its output change as a function of its inputs. Okay, so that is this partial derivative of h with respect to A and partial derivative of h with respect to B. Those are the two things in the black inside that node that you can see. Okay, those two it can compute. And then what it can do is to achieve the computation of the overall, loss or some final output with respect to some parameters or inputs. It can use the locally computed gradients, multiply it with this incoming gradient. Okay, we'll talk about the incoming gradient through the example in the next slide, and then just pass it on to whoever was connected to it. Okay, so you can see that the incoming gradient here is the partial derivative of h with partial derivative of g. G is some other node, maybe later on, h is connected to g. So partial derivative of g with respect to h, that's the incoming gradient. Okay, so what is the incoming gradient? If you really want to think in terms of practice, it's some vector. Okay, or it's a number, a vector. Typically, that's what it's going to be. Okay, that vector is coming in. You have some local computation of a vector or a number. That's partial derivative of h with respect to A, partial derivative of h with respect to B. And then you just multiply them together, and then you can see the red line is just showing, hey, they get multiplied, and then you pass it to whoever was connected to h. Okay. And so that idea was shown. So what are we passing back here? If you just multiply, this is the chain rule. Okay, so partial derivative of g with respect to A is, you can compute it by saying partial derivative of g with respect to h and times partial derivative of h with respect to A, and that's the chain rule there. And we are backward propagating the local gradients and the incoming gradients. And we were trying to go through this example quickly. And so there's a question or a comment here. Please write on the slides. I can't write on the slides because I don't have a stylus. What we can do, let's see. So I'm just going to use I think last time I was using a different app, but I'm going to use just a notepad to kind of mention what I'm saying. So actually, let's go through the example. Okay, so I think so far what I've said seems like too high level. Let's actually revisit this example that we saw last time, just to kind of ground what we're talking about. Okay. There's not much to point in this, these slides, hopefully. And if it's definitely confusing, like Shank, point that out and let's spend more time on that slide. Okay, so it's definitely helpful to the rest of the students as well. They may have a similar question. So let's see. Let's look at this very simple function. Okay, a times b plus c. So the inputs are a, b, and c, and output is a times b plus c. So for any three inputs, I can figure out what the output is. Okay, so we don't even have to think about anything hard here. Now we can represent this computation, okay, as using these edges. You can see three edges, five edges here, and two nodes. Okay, so two nodes that they are, you can see the symbol inside them. So they're doing just that computation. So this node here with the cross in the center is just doing a times b, and this node here with the plus in the center is just doing addition. Okay, now this is an example of a computational graph, and this is just to illustrate, and there's just an illustration, but in general you could have very large computation graph, and we'll see that with deep neural networks there's going to be lots of computations involved, a lot of multiplications and additions involved. But even this example suffices to understand this backward propagation of gradients, okay, to compute our objective. And let me state the objective. The objective is to find the gradient of g with respect to a, gradient of g with respect to, the gradient of g with respect to its inputs, okay, which is going to be a three-dimensional vector, if you want to think in terms of vector, because the three inputs. So it's going to be a three-dimensional vector. Or you can just talk about, hey, what is the partial derivative of g with respect to a? What is the partial derivative of g with respect to b? What is the partial derivative of g with respect to c? Those are three numbers. You can stack them together and you can say, hey, there's a three-dimensional vector. And I think I mentioned that in the slide. Okay, so that's the objective. Okay, so we want to find the gradient of the output with respect to its inputs. Here's a simple input example. How do you find the gradient of g with respect to a? By just eyeballing, you can see that gradient of g, let's say with respect to c, is 1. Okay, you can see that because everything else held constant. How much does g vary when c varies by 1 unit is by 1 unit. So that is kind of clear. And you can actually eyeball what's the gradient of g with respect to a, the partial derivative of g with respect to a, and partial derivative of g with respect to b as well. Okay, but let's actually do it via this backward propagation idea. Okay, so what do you start with? Some base case, which is, hey, let's assume that the partial derivative of g with respect to g itself is 1, which is true. Okay, and let's start from the right end of the graph. Okay, so, and that's informal. What I'm trying to say is that this graph has to have like a forward flow. So you can see that the edges are directed. So a is going into x, into this node, which is a multiplication node. B is also going into this node, and then everything is flowing from left to right. Right. So what we're going to do is propagate backwards. So we're going to start from the last node or the output of the last node and then propagate all the way to the inputs. Okay, what are we going to propagate? We're going to propagate these gradients, and eventually what we want is the gradient of the final output with respect to inputs. Okay, a, b, and c. So we'll start with the base case, gradient of g with respect to g, and we'll look at, hey, what is the local gradient of g with respect to its input? Okay, so let's say its input is called h and c. Okay, so the intermediate, so let's h is equal to a times b. So a times b, let's say this multiplication node's output, let's temporarily call it h. Okay, so therefore this plus node is getting h and c as inputs. So these two blue arrows here at the bottom right, and h plus c is what g is. So right, so that's what's defined in the second bullet point here. So what's the local gradient of this g with respect to h? It's 1. And similarly, what is the local gradient of g with respect to c? It's equal to 1, right? So you can see that, hey, how much does g vary when h varies by 1? It's 1 unit, keeping everything else constant. That's the definition of gradient, right? So once we have this local gradients, what we can do is just multiply with the incoming gradient. So incoming gradient is the gradient of output with respect to itself. It's equal to 1. So we just multiply 1 times 1 and pass it back to the multiplication node. And then we multiply 1 times 1 and pass it back all the way to the input. And therefore, we are done here. In this case, we just wanted to find the gradient of g with respect to c. That's equal to 1. Okay, so that's 1 times 1 is 1. Okay, that's how you mechanically do it. Yes, there's a question. Yes.
So I'm trying to relate it to gradient boosting. In gradient boosting, what we would do is for g, we would calculate the gradient against a, b, and c, right? Instead of going through h here.
Yeah, but right? No, we are still, remember, our objective is still to find the gradient of g with respect to a, b, and c. H is just a temporary name that we
But in this, we calculate it with respect to h, and then we calculate it with respect to a and b. in gradient boosting, we would calculate
Yes.
it directly with respect to A, B, and C.
Yes, so gradient boosting can use this, by the way. So this is at a much more lower level than gradient boosting idea.
Okay.
This is so this is nothing to do with machine learning, right? This is like any computation graph where some inputs are given, any function actually. Think of Python definition, right? You have some inputs and some output. You can always find a gradient of the output with respect to its inputs. Typically, not always, but not all Python functions, but functions like these, you can always find a gradient with respect to its inputs, like the way we are showing here. So maybe we can connect to gradient boosting once we see at least at least one deep learning model, which we'll do in a few minutes. Okay, maybe we can then connect it back.
Okay.
Yeah, so hold on to that thought. Yeah, here, as I was saying, gradient with respect to, sorry, the partial derivative of g with respect to c is done. It's just 1 times 1. Now you can see that the 1 times 1 is the gradient of g with respect to h. Okay, so that we can pass it back to the multiplication node. The multiplication node is going to compute its local gradient of h with respect to a, h with respect to b, and then those local gradients will be multiplied with an incoming gradient. Okay, this is the incoming gradient. This times this actually, but that's kind of backwards. But this gradient here, which is equal to 1. Okay, so local gradients are b and a. Okay, gradient of h with respect to a is b. Gradient of h with respect to b is a. So that's that is we're not it's not new. It should not. This part should not be new. The local gradient should be clear. Now what we're going to do is gradient of g with respect to a is just pick the first gradient of g with respect to itself, and then gradient of g with respect to h, gradient of h with respect to a. You multiply them together, then that's the gradient of g with respect to a. Okay, that's chain rule. So gradient of g with respect to g, gradient of g with respect to h, h with respect to a. You kind of informally you can cancel the numerator and denominator, and you can see that the partial derivative of g with respect to a is equal to b. Okay, that you could have figured out directly from the formula in the previous slide, but this is just a way to computationally do it. Okay. Any questions about this? This is the simplest backpropagation example. There's not much going on except for one interesting node, which is the multiplication node. But you can imagine if there was, hey, there was one more multiplication, one more addition, or one more multiplication. You can imagine how these products, things are getting multiplied and then being passed back from right to left. Right. So let's look at a slightly bigger example. I'm not going to go into explicit details of each computation step, but just to get a feel for like how a gradient is passing again from right to left or from the final output to the inputs. Okay, so in here this function g, a different function, happens to have 4 inputs. Okay, and you can see the functional form of what does g compute given these 4 inputs. Okay, it's something like a softmax. Okay, 1 by 1 plus e to the power or something. Right, that's what it looks like. And they also said, hey, here's a, b, and x and y specific values. Now, given these values, tell me what is the gradient of the function with respect to a, b, x, and y. Okay. Typically, when you compute the gradient, you compute the gradient at a given input. Okay. In the previous slide, the gradients are defined at an input in the sense that the gradient is, you gave me the general formula of gradient of g with respect to a is equal to b. But that's like a general formula. Like, hey, if I give you the value b is equal to 2, you should tell me the gradient of g with respect to a is equal to 2, right? So you need the current values as well to completely define the gradient. It's a bunch of numbers, and so sometimes you need a current value. Yeah. So this function here, 1 by 1 plus e to the power minus ax plus by. This is one example of a computational graph. You don't have to do it this way. For example, here what they've done is. What we have done is put a lot of computations like 1 by 1 plus e to the power minus z as one node here. Okay, you could actually further split it out. Like one node will do 1 by x, the other node will do whatever the output is plus e to the power minus z, and so on. Right. So anyway, so there are 4 nodes here in this computational graph. It's just an illustration, and again you can follow the same mechanical idea. You start with the rightmost node. Compute the local gradient. Okay, local gradient times the incoming gradient. If it's the leftmost node, there's no incoming gradient; it's just 1. So that would be the gradient that you pass back to its parents. Okay, parents is just mean the nodes that are connected to this node. Okay, so the parent of the rightmost node is this plus node. The parents of this plus node are these two multiplication nodes. Okay, just a parent is just again terminology used in the graph literature to just refer to, hey, relation between nodes. So you take the local gradient, compute the local gradients of the plus node, which we know, remember, whatever the plus node's local gradients are just one. I mean, like its gradient with respect to the first input is equal to 1, its gradient with the second input is also equal to 1, right? So then you multiply local gradient with the incoming gradient and pass it back. For multiplication node, also in the previous example, we saw what the local gradient is. That times the incoming gradient is the gradient of the final thing. Okay, but if you really write it down, hey, what are all the things that we're multiplying? You'll see that it's just chain rule. Okay, so you can check up, if you have time, on Wikipedia what chain rule is. It's just a way to compute the partial derivative of a function with respect to its input. Right? So I highly encourage you to figure out what is the gradient of this function with respect to these inputs. Okay, and in assignment 1, you'll see a similar example. So it will be a good exercise to understand whether you multiply the right set of partial derivatives to get to, let's say, the gradient of g with respect to a, for example. So that's what this example is. So it's a worked out example. So I highly encourage everybody to try it out. And if you don't understand, we can discuss in the office hours or after this lecture. So let me step forward. So this chain rule has, we have seen chain rule as like a formula, right? So in previous classes or in previous treatments. Here I'm using graphical notation to kind of cover some additional cases. For example, sometimes a node like h of a comma b may be connected to two different children nodes, and then those nodes may finally result in a final output. Okay, so what you should do is if you have two outgoing connections, then you just add those two gradients before multiplying with the local gradients. Okay, so that's the simple idea here. You just add. And the second example is, what if your gradients are not numbers? Okay, so in the previous two examples of the g function, we saw that inputs are just numbers. Okay, scalars. Scalar or number is the same, means the same thing. But what if your incoming gradient is a vector? Okay, so this can happen. So sometimes instead of the local, instead of the incoming gradient being a number, it could be a vector. So okay, if it's a vector, that means that this h is a vector. Okay, so the only reason why an incoming gradient could be vector is when h is a vector by itself. Okay, so you can think of a function which gives a vector output, right? If h is a vector, and let's say a and b are also vectors. Okay, so I'm just saying, think of a and b as 2 cross 1 vectors, which means they have two coordinates. So a has two coordinates, b has two coordinates. Let's say h also has two coordinates. Let's say they're all vectors of dimension 2. Then the local gradient of h with respect to a is actually called a Jacobian. Okay, it's called a Jacobian, and its dimension is also going to be something like 2 cross 2. Okay, so it's going to be a matrix actually. Similarly, we said, since dimensions are two-dimensional output and two-dimensional input here as well. So again, the local gradient here will be a matrix, which is again 2 cross 2. Okay, so now everything kind of smooths out because the input here was a vector, which was, let's say, 2 dimensions. If it has 2 dimensions, input gradient is 2-dimensional. The local matrix is also 2-dimensional. So 2-dimensional matrix times a 2-dimensional vector is going to be another 2-dimensional vector, which is going to be output. Similarly, here there's going to be 2-dimensional vector that's going to be output. I'm just giving an example of a vector version of what the examples that we saw before. Okay. If we step back, I know we went to a little bit of detail about backdrop, the chain rule idea, but the idea is this idea is very fundamental, is because that's what's revolutionized several pieces of software that you will use in an assignment. For example, PyTorch, and first assignment you'll also use TensorFlow, and there are many others actually. just in the machine learning domain, but also there are others in the other computational engineering domains, where this idea is very useful in trying to optimize functions and do many computational things. Okay, so the idea is we'll step back. Okay, so there was this multiplication of local gradient with incoming gradient and all that. Generally, for a node, right? So for a computational node, what should the software do? So if some software like PyTorch is implementing this backprop trick to compute the gradient of the loss with respect to its inputs, it just has to represent, the model training process or the model itself as a computational graph. And once it does that, each node in that computational graph, as long as you implement two things, which is the forward computation procedure and the backward computation procedure, you should be done. Okay, forward procedure should get its inputs and compute the output, right? That's kind of what the objective of the node is. But it should also compute the local gradient. Okay, like you can, when you get two inputs, you can always compute the output, but you can also compute how much does the output change when the inputs slightly change at the given input values. So you can compute the local gradients. That can be part of the forward procedure. And then if you actually want the if you want to, if it's needed that this local gradient be multiplied with the incoming gradient, that would be part of the backward procedure, where somebody is going to give you some incoming gradients. You multiply locally with your current local gradients, and you pass it back to any preceding or parent nodes, or what you're going to call it. Okay, so that's the simple API. API just means application programming interface, but it just means like a contract of how these nodes are going to pass around information. Okay. So the overall graph is that, overall graph of a computational of a computation, of a function. Let's say the computation of a output or computation of a loss function, loss value, right? And we saw that when we're talking about classification pipeline, given training data, given current model parameters, we can compute the loss, right? So given that that we want to compute a loss given these two inputs, we can draw the graph, and we can have at the graph level a forward step and a backward step. Okay, in the forward step, you recursively compute from the left-hand side, basically compute what all can lead, what all intermediate numbers are needed to eventually get the loss value. Okay, and basically return the loss. And then in the backward step, you kind of start with local gradients at the right-hand side, and keep passing on those local gradients multiplied, keep passing on the incoming gradients, multiply them with the local gradients, and pass it back, okay, to the predecessors or the parents. So as long as you can implement those two key steps, you can actually do backward propagation or compute the gradient computationally. Okay, so sorry, compute the gradient using chain rule. And so once you get that gradient of loss with respect to inputs, then you can just add them or whatever, subtract them from the previous candidate values, and for example, do gradient descent. Okay. Let's skip this slide. It's not saying much. Now let's actually look at sorry, this is not the right one. Let's actually look at an example of this. Okay, and this is actually part of your first assignment. And by the way, this code is available in our repository on GitHub repository. It's just that I've just copied them into Google Drive so that I can open it in Colab. So how many of you have not used Colab? I guess it's hard to answer here online, but Colab is a really nice interface, and I highly encourage most of you to use it as much as possible. Because it does come with potential to use a GPU on the cloud without doing too much setup on your local machines and so on. So what I'm trying to show now is the example of not so much about specifically about backpropagation, but an example where I want to show that the loss regression model that was the only model that we talked about in the last lecture is not sufficient even for a particular 2D dimensional, so particular two-dimensional data set. Okay, so so Colab is very similar to a Jupyter Lab instance if you run locally using Anaconda or even directly. So you just do Shift Enter to navigate and make the cells run. So that's what I've done here. So the first cell is just imports, and hopefully folks are familiar with Python. We are using, and we will be using quite a bit NumPy, Matplotlib in the assignments, for example. And these are just settings. So there's a dictionary of parameters where you can set, hey, what's the size of the figure and so on. Okay, let's talk about data. So we actually don't care about how the data was generated, but we want to look at what is the data. So the two-dimensional data that I kept on mentioning is about this. Okay, it's this, which is, it has basically three classes: a blue, a red, and a yellow class. And you can see that the data is such that it's kind of clear even at this point that maybe a linear classifier, even a linear three-class classifier, which is this multi-class logic regression, will not work. So here's the definition of the model. So the model is, sorry, actually I think I'm running a slightly different model, slightly different notebook. Let me just redo this. Okay, so it's the same data. So now for, I think I just did the same. Okay, so D is a dimension, okay, which is two-dimensional data here, and K is the number of classes, which is 3 here. Okay, so there's 3-class data set. Let me delete this. Okay. And the model, last time we saw x is equal, output is equal to wx plus b. Okay, what is the output? Those are the scores. We have 3 classes, which means we're going to produce 3 scores. Okay. Something like, for example, so scores or score vector is equal to wx plus b. So think of w as like something. Oh, let's actually put in the class in the last lecture. Let's say 1, 2. Think of these as actually column vectors. Okay. So W is going to be something like 1, 1. 2, 3, 3. Some number of rows. So I'm just using the notation very, very similar to how you would have in NumPy. So first row, second row, and third row. Okay, so 3 rows and 2 columns. And X is a let's say it's a column vector. Then you can just do wx plus b, right? So let's say b is equal to, again, let's say for simplicity, 0, 0, 0. So given some numbers like this, you can compute the score vector, right? Let me remove the underscore. So you'll produce a score vector. And this is the model output. Okay. Once you get the scores, okay, how many scores do we get? 3 scores for 3 classes. Then you use those 3 scores to figure out what is the loss of for this example. So this example has this as a feature vector. There'll be a corresponding y, which will say, hey, do you belong to class 0 or class 1 or class 2? Let's say indexing is from 0. So y is equal to either 0 or 1 or 2. Okay, so let me just say y is, let's say, belongs to class 1. Then you can use x and y to define the loss. Okay. So here we're initializing the w and b parameters. So w, again, let's look at let's look at shapes of our data. So our data, we have 300 data points, 300 rows, and 2 features. Okay. Similarly, let's look at w. Actually, let's print out w itself. W here has the opposite, is a transposed version of the w I wrote in the text. Okay, so this W is initialized with 2 rows and 3 columns. Here you can see that I did it with 3 rows and 2 columns. Okay, so the difference is here I'm taking a single X as an input, and here I'll be taking the whole X, multiplying W with X as a matrix. Okay, this is the data matrix which has all the 300 rows, and so if I want to multiply this with W, I have to transpose W. Okay, that's a minor detail that is happening here. Okay, similarly, B is some is a 3-dimensional vector. Okay, so that's some initialization. We also have regularization, the L2 regularization that I was talking about. L2, regularization just means it's the sum of the squares of the parameters that we care about. In particular, we're going to do L2 regularization of this W. Okay, so take the entries. There are 6 entries. So just take the entries, square them, sum them up, and that's going to be your regularizer. Okay. So what we're doing in this cell is the important cell, and in fact, one of your assignment questions is related to the cell. So let's actually execute the cell and then talk about briefly what's going on. So we executed the cell. It's saying, hey, iteration something and some number. So what is that? So here, actually, this cell is implementing gradient descent. Okay? So it's implementing gradient descent from scratch. Okay, which means that it's not using PyTorch or TensorFlow or anything like that. We start with, okay, hey, how many number of examples are there? And this notation should be hopefully familiar to some of you who have used NumPy. Dot shape will give you, the shape of the NumPy array. Here, shape 0 is like the number of rows. And we also choose a step size, which is that alpha of the gradient descent procedure that we have talked about last time. TQDM is just for syntactic, I guess, for cleanliness. I mean, you can get a progress bar like this. We use a package called TQDM. Now, let's do a forward step, right? So what is the forward step? Not a forward step, sorry. Each iteration of gradient descent, we need to start with some old parameters. Okay, the old parameters are, we have some old parameters. These are the old parameters, okay, which we initialized. Given the old parameters, we'll need to do a forward procedure. Okay, that's this. Given the old parameters, hey, W and B, given the data set, I can do a forward step to get to scores. Remember, the scores are exactly here. I'm showing the scores for a single little x, a single observation, single row. But what we're doing here is get the scores for all the rows together. Okay, so there's some vectorization going on. You get the scores, and then we have to compute the probabilities. Remember, from scores to probabilities, there was a softmax transformation, or a e to the power score divided by e to the power all the 3 scores. So that's what's happening here. Okay, and then we are gonna we're gonna compute the log loss. Okay, so this is the cross entropy loss. We are gonna compute that per examples of each of the 300 examples. We're gonna compute the log loss. Okay, and that's where, so this is an important step. This is also vectorized. I suggest everybody look at it in detail after the class or during the break. Once you have that loss per example, you sum them up. Okay, so how do you sum them up? You can just call np.sum. Np is a short form for NumPy. We imported it at the top. By the way, this code I'm following through. If you want to look at it directly at GitHub, you can just look at our GitHub page and look at the code as well. Okay. So you get the data loss. Similarly, regularization loss is, as I said, you have this W matrix multiply with itself. So W star W does element-wise multiplication. Okay, and then you sum them up. Okay, so each entry you multiply with itself, it's going to square it, and then you sum up all the entries. Okay, multiply with this regularization coefficient that we chose. Okay, some coefficient value. This is just some constant. Don't worry about it. It's just a constant that we picked. And 1/2 is again a constant that was chosen for simplicity. Okay, it's not important that there has to be a factor like 1.5 here. Okay, I mean that factor will help you have the definition of the gradient in an easy way. So loss, overall loss is the data loss, L data plus L regularizer from, if you remember from last lecture. Okay, so till all these steps, what we did is a forward procedure. Okay, so for the given candidate model parameters, we computed the loss, okay, some loss number, and we are printing it out every 10th iteration. So this numbers that we see here are the loss, at the 10th iteration of this gradient descent step, at the 60th iteration of this gradient descent step, this is a loss, and so on. So you can see that loss is decreasing, but it's not decreasing too much. It's from 0.91 to 0.86, sorry, 0.78. So that's what we're doing. Now, here's the interesting part. Okay, this is where we actually are doing backprop in a way. We are actually computing the gradient of the loss with respect to the parameters. The parameters are W and B. So the gradients are being captured in these variables. Okay, dW and dB, just variable names. They are trying to capture the gradient of the loss with respect to the W parameter, gradient of the loss with respect to the B parameter. Now remember, B is a vector, which means that the gradient of the loss with respect to B is going to be a vector. Okay, and in fact, B is three-dimensional, so this variable dB is going to be three-dimensional as well. Now, what about the gradient of loss with respect to W? W is a matrix. Okay, W is a matrix. You can see it's either, let's say, here it is a 2x3 dimensional matrix, which means the gradient of the loss with respect to that W is also going to be a 2x3 matrix. Okay, so that's we will not exactly go through why you should. This is a part of your assignment, so I'm not going to discuss that here at the moment. But the previous three steps somehow achieve, actually all these steps, these 5 steps, achieve computing the loss, computing the gradient of the loss with respect to its inputs, which are these parameters. Okay, and they are actually using backprop, the same chain rule idea that we saw. Once you have the gradients, actually there's one more minor addition to the gradient of the loss with respect to the W parameter, which is the this was the gradient with respect to the loss data part. This is the gradient with respect to the loss regularizer part. Regularizer's gradient is actually this, and so you sum whatever the previous value is, you sum it up with an extra thing, and that's the gradient of the overall loss with respect to W. But once you have this gradients, okay, this is the part which is computing the gradient of the loss, overall loss with respect to its inputs. This is the step where gradient descent is happening, and we have seen this in equation in the lecture, in the recap part, in the optimization part, which is what is the previous value, subtract some learning rate, or whatever it's called step size, minus step size times the gradient of the loss with respect to that parameter. Similarly, similarly the second line as well, B is equal to, we can write just B minus step size times the gradient of the loss with respect to B. Okay, it's the same idea. So this is the gradient update. So these lines are for computing the gradient. These lines are for just computing the loss, like the forward step. This is a backward step, and this is the gradient update. Okay, and you can see that this is the output that happened to be generated. Any questions here?
Professor, I'm just checking your GitHub.
Yeah.
This code, it's slightly different. You use a TQDM range, and you're in the GitHub one, it's just simply range, gradient descent loop.
Yeah. So you can drop it. Actually, it's not needed.
Oh, okay. Oh,
it's just a beautification code. You might have seen you might see this in example code. It was just to kind of show progress. Okay, and typically if your loop is takes a lot of time, then you'll actually see slowly it's progressing, so that you have a sense of.
Oh yes. Okay, got it. Thank you.
Yeah, it's not needed. Let's actually rerun it. If you rerun it, of course, it started from that value, so there's not much update here. But if you start from some random value of the parameters and then run this cell, then you start with some high loss value, and hopefully you get to some low value, and it kind of has stabilized, right? It's not changing. Of course, if you change the step size, you will see all sorts of behavior. I don't want to spend too much time on that. Where is the step size choice? I think step size and stuff like step size is actually 1. Instead of that, if I make it 10, let's say, it's going to be pretty bad. So it started from whatever the previous value was of loss, and then it kind of is diverging. It's actually seems like it's stabilized, but it's not the loss, right? I mean, you know that the lower point was this, but you kind of went away from the lower point. In fact, let's actually play with that. Let's put 100. Yeah, it's going to explode. Okay, so it's going to just go all over the place. And you know, sometimes it's just oscillating all over the place. Okay, it's not doing actually the descent. Well, actually, let me get back to 1. Or yeah, so now you can see that it's actually going down. It's actually not good. We should probably spend more time here. I think I want to get to 0.7. Okay, so this was roughly what we had. Now, yeah, so now what I want to quickly show is this is just a glue code to just, it's actually not something that you should do, which is I'm just saying that the train data is also the test data, and I'm just getting the predicted class labels and seeing if the class labels match. Okay, so it's just looking at, hey, is the predicted class label the same as the true class label? It's just saying, hey, 50% of the time I match, 50% of the time I'm not matching. In fact, if you look at the decision boundaries, you know, it's a 3-class classification problem in a 2-dimensional space, so you can actually visualize the whole space. So you can see that the 3 classes are actually the decision boundaries are these edges between the 3 regions. Okay, there's a blue region, there's a yellow region, and there's a red region. That's what the classifier has learned. Okay, so the classifier has learned, hey, this anything below this boundary and anything to the right of this boundary should be red. But you can see that there are other reds there, and there are reds in the yellow region as well. So this is just an illustration of you know, why linear models are sometimes not enough. Okay. Any other question? Okay, so I think I just explained the same thing. So I'm going to flip these slides because it's the same stuff. Okay, so now what we're going to do is resume from there and improve on this result. Okay, so this result that we have gotten so far. Okay. And this, by the way, should match what we talked about in lecture 1 in terms of the model that we're using. Okay, so it's exactly, you can see here, it's just wx plus b. It's just vectorized here, but otherwise it's just wx plus b. Okay, that's the model. And this is actually exactly multi-class logistic regression. So if you didn't want to import scikit-learn, if you didn't want to import other packages, or even didn't want to do it in R, this is complete code for doing any like 3-class multi-class logistic regression. You can change it to 5-class, 10-class, whatever is needed. Okay. Yeah. So the outline, I'm going to skip one part, which is Python walkthrough, and this is something I've learned that it's generally not necessary. But if you strongly want us to do a walkthrough, we can do a walkthrough. Either here, I mean, I would suggest not doing it right now, either through talk to the TA if you want a quick primer on Python, because we just went through a Python code and it was not basic, right? We were already using matplotlib and NumPy, for example. You can talk to the TA if you want a one-on-one session, or with me if you want a one-on-one session. Okay. So I'll try to skip that for now and see how things are. So I will skip some of this. I do want to not skip one thing, which is I'm going to, hopefully today I'll have time, and I'm going to give you a brief example of using PyTorch. Okay, so that you're a little bit more, it's not needed for assignment 1. In assignment 1, you actually use a TensorFlow/Keras. But as an assignment 2, PyTorch is going to be super useful. So in the next, maybe next 2 or 3 weeks, as you have time, try to be more familiar with NumPy. And in fact, assignment 1 will make you do that, because you have you'll have to fit a feed-forward neural network. But hopefully, today's demo of PyTorch, which I'll do soon, will also get you primed to understand how PyTorch works. Okay. So yeah, so what I'm going to do is now extend the model that we saw, the multi-class logistic regression model, or just a linear model. I keep calling it linear model because it's a linear model because it essentially gives us linear addition boundaries. Okay, so and you saw the linear addition boundaries in the previous in that collab notebook. So we're going to extend that. Okay, so one extension, and we're going to and this can be generalized, easily extended in other ways. But here's an extension. Okay, we're going to call it a 2-layer model. Okay, the model is as follows. It's going to have Now instead of w comma b, it's going to have w1 b1 and w2 b2. It has like a two sets of w comma b pair. Okay, and so it's a function. So if you really write it in terms of like a function, so it has, if you think of Python def function, then it has 5 inputs, right? So one, x is itself the input, the feature vector, and then there are 4 other inputs. Okay, and given all of them, you can see how the computation happens. First, x is multiplied with w1 and then added with b1. That's almost the same as, it's in fact exactly the same as what linear model will compute. Then there is a kind of new operation going on, which is like a max of 0 comma the scores vector, or max of 0 comma whatever was the output of w1x plus b1. Okay, we'll see that we'll see in the next couple of slides what this operation does. Okay, in fact, the operation what it does is gives us a vector, and that vector again is multiplied with another matrix, and then another vector is added, and that's the final scores. Okay, so we're gonna disambiguate each one of these steps in the next couple of slides. But first, I want to quickly point out a few things. X is d-dimensional. Let's say it's 2-dimensional. X is 2-dimensional. Then you can actually, and let's say you're doing a 3-class classification, very similar to the example that we saw. Then you should be able to say what is the dimensionality of W1, what is the dimensionality of W2. Okay, you should be able to say if some extra information is given, which is what is the number of hidden nodes in this 2-layer model. Okay, so I'm now using some specific new terminology. I'm saying it's a 2-layer model, and I'm saying there's hidden nodes. Okay, we'll come back to this, but all I'm trying to say at this point is that knowing the output dimension, which is like 3 classes, and knowing the input feature size 2 classes, feature size is 2-dimension, is not enough. You need one more number, and that number is let's call it Q. Okay, so that number is going to determine the size of W1. That number is also going to determine the size of W2, in addition to the number of classes and the input size. Okay, so but this terminology, we're going to really spend a few more slides on this, so it will become clearer. Okay, let's talk about one thing at a time. So let's talk about that max of 0 comma some input, right? So that was one part of that formula. In general, all these functions, okay, these functions are broadly termed as non-linearities. Okay, non-linearities. So if there is no non-linearity, then what I'm trying to write in the middle column are all these non-linearity functions. Okay, functions which implement non-linearity in neural network models. The first one is there is no non-linearity. The function is identity function, right? Whatever is the input, just output is the same. So that's not a non-linearity. But all these others, in particular, the ones I've highlighted in blue, are examples of non-linearity functions that are used to define a neural network. Okay. In particular, in the previous slide, we used the last one called ReLU. Okay. ReLU, y is equal to max of 0 comma x or x comma 0 is the same thing. And what does it do? It has 2 inputs. So it has one input, right? X, right? This function has one input x. It takes x. Let's say x is a scalar. Then you just compare x with 0. And if x is greater than 0, then output x. If x is less than 0, you output 0. Okay. So we'll see a picture in the next slide. But let me answer a question that I did not answer earlier, which is how do we choose the step size? I think, I guess that relates to this. I just changed the step size and a lot of things didn't work, right? So that is unfortunately an art. You can see that with the last step size, it is not at all. It's going up, going down. It's going down again, going up, and so on. So it'll blow up. Okay, the optimization will not work. So choice of step size. There is some work in trying to judiciously, in a principled way, choose a step size. But in practice, you just try out a few choices, just like you choose the regularization size when you're doing, let's say, regression or something. So a priori, I mean, there's no good recommendation at this point. Okay, let me come back to where I was. I was talking about nonlinearity, right? So let's focus on these 3 actually in the next slide. But in this page, you can see there are lots of nonlinearities, and in fact, in assignment 1, you will implement one of these. So let's see. Let's start with 1. Okay, so we'll get to the max of 0 comma x or x comma 0 in a second. Let's start with one of them, okay, which is called sigmoid nonlinearity, 1 by 1 plus e to the power minus x. So what is a sigmoid nonlinearity function? Okay, it's just a function. Think of it as a scalar function, which is like I pass in a number, let's say 2.3, and I get a number. Okay, so if you pass 2.3, you get almost a number, let's say 0.9. If you pass 0, you get a number 0.5. Right? So it's a one-dimensional function. So it's a function whose output can only vary between 0 and 1. That's how this function is. You can just eyeball it. So let's say I take x is equal to let's say I take so this is a function 1 by 1 plus e to the power minus z. Z is the input and output is 1 by 1 plus e to the power minus z. You can imagine, hey, if I set z to infinity, like or whatever 10,000 or 100,000, what is going to happen? E to the power minus 100,000 is going to be a really small number, right? But still positive. And 1 by 1 plus a really small number is going to be just 1. Okay, so for z is equal to 10,000, it's almost going to be close to 1. Right? So that's what's going on. You can see the right hand side of this plot on the right side that I'm showing you. Okay. Similarly, if z is let's say minus 1,000, or in this plot it's let's say z is minus 6, then e to the power minus of minus 6 is e to the power 6, which is a large number. So 1 by 1 plus e to the power 6 is going to be a number which is very close to 0. So you can see that this function traces like this. Okay, so this is a nonlinearity that you can use in a neural network model, in particular feedforward neural network model that we're going to see here. Okay, so what's the purpose of this nonlinearity? It introduces it's nonlinearity is exactly this, right? So the relationship between input and output is not linear anymore. So output is not the same as not scaled the same way as input is scaled. Okay, so there is different gradients at different parts of the input. Right, at 4, the gradient of output with respect to input is going to be close to 0. At 0, gradient of output with respect to input is, let's say, close to 1, 45 degrees, and so on. Okay, so by introducing these functions into the mix, we are now making our model richer. Okay, and that's the purpose of these nonlinearities. Let's, in particular, the sigmoid nonlinearity that we're seeing here. So on the left side, I'm just showing you the usual gradient update procedure. So if you have an incoming gradient, if you have a local computation node like this, you just multiply the incoming gradient with the local gradient and you just pass it back. Okay. From the curve, you can see that it's not zero-centered in the sense that at 0, the value is 0.5. It's in contrast with the tanh function that I'm going to show next slide, where at 0, the value is 0. Okay, it's just two different functions. Now, because this function is not zero-centered, if we do gradient descent of the loss with respect to inputs, and if this function is somewhere in between, this node is somewhere in between, it may affect the gradient descent procedure. Let's maybe we'll revisit this point later. But right now, for right now, all I'm trying to say is that if there is such a node in a computational graph, and remember, every model and training loss forward step can be represented as a graph. If such a node exists, then this it will affect the gradient descent procedure. Okay. Okay. So the zero centering comment that I made is just to contrast with the tanh nonlinearity. It's just another second example of nonlinearity that we'll look at right now. So in the plot here, actually focus on the dashed line. Okay, ignore the green line and the yellow line. This is, I think, we got it from Wikipedia. But basically, focus on the blue line. It's actually dashed and a little bit lighter. It looks very similar to like an S, right? Which is similar to what the sigmoid function also look like. The only difference is the tanh function can have an output range from -1 to 1 instead of 0 to 1 that you saw in the previous slide, and its input can be any number. Okay, so it's again a nonlinearity that you can use in a model definition. It turns out, and this is a teaser, that these two functions, okay, they're not the at least in 2022, they're not the best functions to use while defining a neural network model. Okay, and that's because these functions have. Let's look at this function. These functions, when inputs are large or small, like in this figure, you can see that if input is smaller than -6 or the input is greater than 6, the gradient. Okay, how do you visualize the gradient? It's like think of drawing a line on top of this line at any given point. Okay, you can see the gradient. How much does output change when input changes from 4 to 6? Doesn't change much. How much does the output change when input changes from -6 to -4? Not much, right? So gradients are 0, at these values. And the gradient is only meaningful when the input is, somewhat small, okay, within a small range. And same thing is here. You can see that for a huge amount of input values, its gradient is almost 0 or 0, and here also it's 0. Okay, so if gradients are 0, then you can imagine if I'm doing back propagation and there's a computation node which local gradient is 0, whatever was the incoming gradient times 0 is going to be passed back. Right? So 0 times the incoming gradient is again 0. That's going to be passed back. So those are the issues that you'll face if you use these non-linearity functions when you're defining the model. Okay. And so coming back to the original picture, so in the 2-layer model example that I gave 3 slides back, I used this nonlinearity, which is max of 0, x. Okay, max of 0, x and max of x, 0 is the same thing. So it's like this, right? So max of 0, let's say x. Okay, so remember the x is the same as, let's say this is the x. Okay, let me say x is equal to -1 and 2. So max of 0, x is going to be a vector which is going to be 0 and 2. Okay, so input is a vector, output of this function is a vector. Okay, so this is, let's say y is equal to max of 0, x is equal to a vector, which just basically takes each coordinate and says, hey, compare it with 0. Is it greater than 0? If it is greater than 0, just output it as is, which is 2. If it is less than 0, just output 0. Okay, that's the function. And that function has a curve which looks like this blue line here. So again, input is x-axis and the output is on the y-axis, and you can see the blue line, right? So anything less than 0, your output value is 0. That's why you have a flat blue line at the bottom. And any value which is greater than 0, you have a 45-degree line. Okay, so this blue line here. So ignore the green line, and so it's actually, so this nonlinearity is at least slightly better perhaps than the sigmoid or tangential nonlinearity that we saw earlier, in the sense that at least on the positive side, the gradient doesn't vanish. Okay, in the sense that, hey, what local gradient, if its input is positive, then the local gradient is actually equal to 1. Right? So whatever is the input gradient times 1 is what is going to be passed on to its predecessor or parent node. Okay. But of course, if x is negative, then you multiply with 0 and pass on 0 to its predecessor. So there's still this aspect of making the gradients vanish or making the gradient 0, but it has a little bit different mechanism. At least it's not making 0 on both sides, for example, when the input is both positive and negative. And so this is the nonlinearity that was defined in that 2-layer neural network. Okay? So in the 2-layer model and neural network, I'm just going to use the word interchangeably. So here's the same model that I gave the expression for 3 slides ago, which is in the bottom. Okay, so the bottom blue box, I'm showing the same model. Okay, it has the W1, B1, W2, B2 as the 2 arguments. And its computation is W2 times max of 0, some vector plus B2, and that some vector is W1x plus B1. So now let me revisit the terminology. 2-layer neural network, right? First of all, we're going to have a illustration of this model which is the bottom blue box, in terms of layer, in terms of a layered view. Okay, that layered view is on the right-hand side. Okay. So we'll have an input layer. Okay, I'm gonna say what this is, but we'll have an input layer, we'll have a hidden layer, and we'll have an output layer. Okay, so so there's an input layer, there's a hidden layer, and there's an output layer. So it's called a 2-layer neural network or a 1 hidden layer neural network. So it's 2 layers because you can see I'm trying to draw a picture of this function. So I need inputs. So let me represent inputs to the left-hand side. I'm going to use, let's assume that input is 3-dimensional, okay, for simplicity. So then I'll draw 3 nodes on the left-hand side in one layered view. So like one node below the other, okay. And then I'm also going to draw the outputs. Let's say we're doing a 2-class classification. Then the outputs are also arranged one below the other in a layered type of a view. And I'm going to arrange a few other nodes, okay. These are what I call hidden nodes, okay. I'm going to only have one set of such hidden nodes because I have a 2-layer neural network, okay. And the number of these nodes is exactly that dimension thing I was talking about, which is missing, the Q parameter that is missing. Here I've just chosen the number of hidden nodes to be 4. Okay. It's 2-layer because although there is input, hidden, and output, so just think of these edges as representing layers. So input to hidden is 1 layer, hidden to output is one more layer. Okay. But if you actually ask how many hidden layers there are, there's only one, okay, which is the hidden layer is the there's 1 hidden layer or 2 layered network. Okay. So these orange things are nodes. So non-linearities are going to be in these hidden nodes, okay, in these hidden nodes, and we're going to open up this hidden node in a second. And the output of these hidden nodes are also called activations. So these are all just terminology, but if you want to start from the ground up, this is the function. Okay, this is the function. So X is the input. Let's say X is 3-dimensional. These are 3 dots. The 3 dots get multiplied by a matrix plus added with a vector, and whatever is the result, right? That result with a non-linearity is the output of these 4 nodes. Okay, so why are there 4 nodes? Because let's say the number of rows of W1 is 4. Okay, number of columns of W1, let's say, is 3. Okay, then this makes sense. This multiplication makes sense, and having 4 outputs makes sense. Those 4 outputs are then, that would be the output of this hidden layer, which would this activation vector. That times a W2 matrix plus a vector addition will give you 2 outputs. Okay, that means that W2 has the number of rows to be 2 and number of columns to be 4. Is that clear?
Can you repeat the last part, please? Number of rows will be
yeah,
2.
let's actually good point. Actually, I was thinking about the same, that perhaps I should give a quick example. So let's say W1, B1, W2, and B2. These are the 4 parameters. Okay, so pairs of parameters. W1, B1 would be very similar. So let's say this is a matrix of size 4 times 3. Okay. Now X is 3-dimensional. Okay, just because in the picture it's X, we wrote three orange circles. So let's say X is 3-dimensional. W1 is a matrix of size 4 times 3, and B1 is also going to be a vector of size 4 times 1. Okay. Let's go back to the picture. So all I'm saying is, so X is 3-dimensional, W1 is 4 times 3. You can multiply. What do you get? You get a vector which is 4 times 1. You add another vector which is 4 times 1. So you get a 4 times 1 vector, right? Is that clear? So what I'm saying is this max of 0 and W1 X plus B is a 4-dimensional vector. Actually, X and multiplication seems similar. So let me just change the X as 2 stars. This is better. Oops, sorry, there's another X there. Is this clear? So I'm just relating it to the picture. Okay, in general, doesn't have to be this. This is a running example of that picture. Okay. now W2. So we, in that figure, we have just two outputs, right? Two scores. So that's why I'm saying that W2 should be a matrix of size 2 times whatever is the input. The input vector is 4 dimensions. So I have to multiply it with the right size, right? So W2 has to be 4 dimensions so that I can multiply it with W2 correctly, right? And similarly, B2 has to be a vector of size. Okay, who can tell what the size of B2 should be?
Two.
Yes.
2 cross 1.
Yes.
2 cross 1.
2 cross.
Yes, many of you have given the answer. That's good. So it's just with two times 1. It's basically something. So once you multiply W2 with a vector like this, okay, what do you get? You get a 2 cross 1 vector or two-dimensional vector. And then you have to add it, right? So that's what this computation is saying. Hey, whatever you compute, add a vector, right? So what we computed is the 2-dimensional vector. Then we can only add a 2-dimensional vector. So that's why B2 is 2-dimensional. So this is just to match dimensions. Okay, this is just something like a homework, and there's something that you may have to come across a couple of times, especially when you're setting up these neural network models in PyTorch or TensorFlow. Although these days it makes it a little bit easier, but still something that you will have to at least think about. Okay, in fact, there was a design choice that was made, which was not available when you're doing linear model. Okay, which is how many hidden nodes? Like, why is this 4? Okay, why can't it be 8? Okay, we can choose 8 in the center. Input dimension is fixed because the number of features is fixed. Output dimension is fixed because number of classes is probably fixed in your data set. What you can change is just which is something of a model configuration, a model architecture choice, is how many hidden nodes should be there. Okay, and there is no good answer as such. The more nodes you have or the less nodes you have, it just changes the performance of the model depending on the data set that you have. Okay. And 2 layers, exactly, because you can just think of 2 layers as like 2 sets of these black edges here, and that's why it's 2 layer. Or if you really want to think of 2 layers, you can just ignore one of the degenerate layer. Input is really a degenerate layer. So you have a hidden layer with a bunch of black edges, and you have an output layer with a bunch of black edges coming to it. So those are the 2 layers. Okay. But how many hidden layers there are? There's only one, because there's only one bunch of hidden nodes and edges coming into them. Okay. Now, what are these edges? These are exactly the type of this looks like a computational graph. It's not exactly a computational graph, but it pretty much looks like a computational graph. Okay. Okay, so I guess I said the same thing earlier. So there is some choices to be made, which is why stop at 1 layer? Okay, in the previous example, I just did 1 layer, but you can imagine, I mean, don't have to think in terms of this expression in the blue box, but in general, you can say, hey, what if I add 1 more hidden layer? What if I add 1 more hidden layer? Right? You can do that, and then you have a much crazier looking function, much more complex function. And so that type of function may be able to deal with decision boundaries, for example, which are not linear. Okay, so for example, that spiraling data set that we saw, maybe once you had a hidden layer or 2, you can actually have you are able to get better decision boundaries, and so you're able to fit the data better. Okay. And so some questions is how many number of layers and how many hidden nodes or hidden units in each layer. Those are questions that we don't have good heuristics here. It is something that you want to search how much, because if you choose these numbers to be large, then you may be completely overfitting to the data. So if you choose too small, then it may be almost very similar to linear model performance. So I want to wrap up Feedforward network with the, I don't think this slide is saying much. It's exactly the same as before. So instead of doing backdrop and just finding the gradient of the loss with respect to 2 parameters, you need to find the gradient of the loss with respect to 4 parameters. Okay, yeah, and nothing else changes. So you just update the parameters, these 4 parameters now, in the direction of the negative gradient. Okay. Why is it negative gradient and why not positive gradient? That's because we're doing gradient descent to minimize the loss. We want to minimize. So every time we pick new parameters or iterate over, new parameters should hopefully lead to lower values of the loss, and that's why we're doing in the direction of the negative gradient. Okay. Yeah. So let me quickly show. I will not spend time on this code. Okay, and that's why I'm trying to show it and then take a break, is because this is part of your assignment number 1, to understand this code and to do some, try out this code, and do some extensions. Okay. And so I'm only going to run this code just to give you a sense of, hey, we do improve on the previous linear model because we introduced nonlinearity. So here, exactly as is shown in lecture slides, we have a new set of parameters, okay, an additional set of parameters, which is W2 and B2. We didn't call the original ones W1, B1, but we could have done that. Okay. And here the number of that 4 that I was talking about, 4 as the choice in that illustration. Here, I don't know how much we choose. Oh yeah, we chose 100 as the number of hidden nodes. Okay, and we'll see if we can change it to 4 and if it works. So the next step is exactly very similar to what we discussed in the previous logistic regression case, but it has a few more lines here. So that's part of the assignment. So I will not elaborate at this point. So you can see, I mean, the loss is already like fixed to 0.24, and at least the initial number was up higher, and then it came to this value. Yeah, let's get the accuracy. It says 0.98. Okay, it was very different from 0.5 accuracy that we're getting, and this is the result that you see. So your decision boundary is nonlinear. It's able to try to capture almost all the blue dots in the blue region, all the red dots in the red region, all the yellow dots in the yellow region. Okay, and you can also try, hey, why did you choose 100? Why is the number of iterations like 10,000? Change these. Why is the step size? Why is the regularization value this much? Why is the step size still 1? Why is it not 0.1 or something? So you can change this, and then it may affect the loss value you get. But here you can see that it's almost accurate. So maybe you may increase the accuracy to 100%, perhaps. But you can see that it is an improvement over the previous linear model in the synthetic data set. So let's take a break here and resume at 5. Okay, and if you have questions, put it in the chat. We can discuss it right after the break, or stay back and we can discuss it right after the class. Okay. I'm gonna pause for 10 minutes. Okay, so let's resume the lecture. So I just skipped over a couple of slides, which is screenshots of the code. But I wanted to, so the code, I just mean this final figure where we saw the decision boundary now is nonlinear, thanks to that nonlinearity that we used. And in particular, I didn't point out the nonlinearity, but we used, I think it was the ReLU nonlinearity that was used, or the max of 0,1. Okay, so there's a link here that I'm just going to discuss now to kind of get more intuition about whatever we've covered so far. So let's do that. So the link is this playground.tensorflow.org. And if you click on that, you get to a page like this. And here you can see actually, you can actually do this gradient descent based optimization in the browser. And you can see what happens, what's the dimensionality. And we know we walked through a very short example earlier. For example, here you can see there's 2 features. And it's a two hidden layer neural network. So in fact, let me reduce the number of hidden layers. So are they using a different terminology? Okay, I guess terminology is slightly different. Okay, let me reduce the, yeah. So this is the linear classifier situation. So let me actually pick a data set. So on the left-hand side, you can pick a data set. In between, you get to choose a model. And then at the top, you can choose some parameters of the model. And then you can click on this play button, and it will actually try to optimize, and you can see the decision boundary. And this is all done in the browser. Okay. So let's start with the left-hand side. We picked a simple data. And features, we picked 2 features. Okay, so let's say a feature like this and a feature like that. and there are no hidden layers, so it's not a neural network. I mean, sorry, it's a neural network with zero hidden layers. So input is directly getting mapped to output using, let's say, w comma b. So it's like something like wx plus b, and output is like this. So you can already see that the output is, you can see that two classes are separated. So if you train this model, you can already see the loss, which is this L type of thing that you see here, is already 0. Okay, so you perfectly separated the orange dots from the blue dots. Okay, so let me pause that. So instead, what if we had a data set like this, okay, which has orange dots on two sides and blue dots on two sides, right? So this one, if I try to train, you can see it's taking a lot of time. You can't see the decision boundary that well, but let me pause it, increase the turning rate to 1, and you can see how it's saying decision boundary is here, okay, which doesn't, which is not the best, right? Because blue are all on the one side, but then there's a bunch of blues on the other side. That's what's leading to somewhat of a high test loss. Okay, test loss is a darker color than training loss here. So this is something you can experiment. So this is what we illustrated one using Collab, that just a multi-class logic regression is not enough, okay, even for two-dimensional data sets. Now let's see what we can do. So we can add one hidden layer. Okay, so this is the hidden layer, and let's actually make it similar to our illustration. So there were four hidden nodes, right? Four nodes in the hidden layer in our illustration. Let's add one more input, which is x, three-dimensional input. It's not exactly three-dimensional input. It's as you can see here, it says x12. Actually, let me use something simpler. So sine of x1. So it's just feature engineering. The original features were 2 dimensions, x1 and x2. We just changed we just added an extra feature just to say it's 3-dimensional. It's sine of x1. Okay. Now we have 3 input features, 4 hidden neurons, and then output is 2 class. Okay, as you can see, the 2 classes are the orange class and the blue class. Now, I didn't change much. So activation, you can change between those, like the ReLU is the one which is max of 0, x. There are other ones that we have discussed already. Learning rate is exactly that coefficient in front of that gradient update. If you want to add regularization, you can add regularization, and regularization rate, you can choose something, and you can train. Okay, and you can see what the decision boundary is. It's non-linear, right? And it's able to, at least on training as well as test. And test, I don't know if we can see the test data, but basically this is the fit model. Okay, and this is much better and probably different. Yeah.
So sorry, like you were going a little ahead. So when you selected the features x1, x2, and sine of x1, what did you mean by there are only 2 inputs? I mean, the original dimension is 2, and you've added an extra dimension?
Yeah. So this is something good question. So this is I added an extra dimension, which is just feature engineering, right? If you remember from linear regression or from other machine learning classes, you can always create from raw features. You can create derived features like x square, log x, sin x. Sin x is what I added here. And the reason I'm saying it's a two-dimensional data set is because you can see the data set. The data set is exactly x value being between -6 to 6 and x1 value being -6 to 6, and x2 value being -6 to 6 as well. So that's why you're able to visualize it from like in a 2D plane, right? That's the original features. Although we added 3 features on here as input, the third feature is just a derived feature. We can drop it. It's just for trying to conform it with our illustration, which had 3 nodes there. If I drop
we don't really need it. We're just adding it to see what the impact is. Okay.
Yeah, we don't need it. We added it only because I wanted to have 3-dimensional input. Yeah. I mean, let's train here, right? So if you train here, so you almost get you got something different, but different type of decision bound, different nonlinear classifier. So it's like, by the way, decision boundaries don't have to be connected. Okay, that's you might see that in linear case, one side is always going to be orange, one side is always going to be blue. But with more, with different types of data sets, the decision boundaries, with more nonlinear models, the decision boundaries can be separated. Okay, like for example, let's look at this one, right? Let's train this model. So here, clearly the decision boundary has to be, actually it's not separated, but at least it should look like a circle, right? So let's train this for this data. or maybe not a circle, but close to a circle. But you can see that the decision boundary is like this. So it's not like separating the plane into exactly two half planes. Okay, so it can be a closed region is one class and the other region can be a second class. This is not something that you can see with a linear classifier. Yeah, so here in this playground.tensorflow, you can only do two dimensional because that's the illustration. So these other features are just not needed. You can actually add them. So actually, that's a good question. So we can actually drop all these neurons, keep the classifier linear, and now let's add all these features. Okay, all these derived features, and then say let's use this this two-dimensional representation where we know that if we didn't have these features, then we can only get a linear decision boundary, and it will not do well, right? But here with these extra features, you can actually do well. You can see that there's a circle. You can actually get this nonlinear decision boundary in the 2 dimensions. Of course, in the higher 7-dimensional feature space, it's going to be a linear. It's going to be a hyperplane. It's going to be a plane type of thing, which is splitting between these two classes.
So this kind of feature engineering without a hidden layer is similar to support vectors. Is that what it's doing?
No, in support vectors, you still have to do feature engineering. Yeah.
Yes.
Yeah, it's
like
support. Yeah, it's extra features. Oh, good point. Good point. Yeah, support vectors with kernel is going to do something like this in a higher dimension.
Okay.
Yeah.
Isn't dbscan do the same thing?
I thought dbscan is slightly different, right? So I'm not aware of it to answer in real time. But let's maybe discuss about dbscan after the lecture.
Okay.
Yeah. So these extra features are exactly what you would think of. And if you didn't know deep learning, right, it's not related to deep learning at all. It's just whenever you have raw features, you can always create additional features for more interpretability, or to make is another lever to make your classifier nonlinear. So if you are restricted to only doing linear regression, or if you're restricted to only doing, let's say, multi-class logistic regression, but you want nonlinearity somehow, you can always increase the number of features, like take squares, make polynomials, right? And instead of x1, x2, say x1 square, x2 square, x1 times x2, things like that. And then you're essentially kind of doing linear regression in a higher dimensional space. So which is like in this case, you're doing basically logistic regression in a 7-dimensional space here in this example. It's just that in the 7-dimensional space, you actually have a linear decision boundary between the orange class and the blue class. It's just that in 2-dimensional projection, you can just see a circle. And this is very similar to what the other student who said, it's related to SVMs and using a kernel, for example. If you just use raw features, but if you use a kernel, you're essentially doing that, going up in Hammer dimension and trying to fit a linear model there. Yeah.
Professor, how do we decide like which activation function should be used in particular models?
Yeah, that's a great question, which I don't have a good answer for, other than saying that this evolution of all these activation, these non-linearities, sorry, or you can also call it activation function, as you said. It's just that people tried, empirically, how hard it is to train such a model. Okay, so these non-linearities actually mess up that gradient descent procedure. Okay, so remember, if it was without these activations, if it was just a linear regression, if it was just logistic regression, you can the optimization loss function looks like a U or a parabola, or like a basically looks like a U. So you can only, if you do gradient descent, you can actually get to the bottom of the valley and get to a low loss situation. But the moment you add these nonlinearities, you actually get these multiple peaks and valleys. If you think of like illustratively think of the loss function, and so this choice of this activation influences how well you can get to an appropriate valley, and so how well the model fits data. Okay, and so empirically, folks have kind of converged onto, like, for example, these 3, and that's why you see these 3 options here instead of all the 20 options in the slide that I showed you. But people, tend to change it. It seems to not have too much impact, other than helps with training. But it does certainly improve. Definitely having ReLU, for example, influences what you can get, right? So most default choice seems to be ReLU, this max of 0,x, which is what we saw in the illustration. But the other ones are also still valid. Okay, later on we'll talk about LSTMs or a certain type of neural networks where we still use tanh nonlinearity, for example.
Okay, thank you.
Any other questions? Okay, if not, let's actually move. So what we're going to do is feedforward networks, although we only spoke about one hidden layer, you can just imagine, hey, in fact, in this illustration, you can actually add like, 4 or 5 hidden layers, right? So it's the same idea. So instead of, matrix, so instead of W1, B1, W2, B2 pair, you'll have W3, B3 pair, W4, B4 pair, every time you add one extra hidden layer. Okay. So otherwise, everything else is same terminology. There's no extra, consideration needed. Okay. I mean, of course, training that, the more hidden layers you add, it's harder to train. Okay. And that's exactly what I was saying, that you'll have, especially with non-linearities, you'll have like peaks and valleys, and so gradient descent will not work. And so the huge challenge, and why deep learning was not, the popular thing maybe in 2010 or 2000, early 2000s, is because it's hard to train without, without enough compute and without enough data, and people trying out, hey, how to train these networks, and converging on some good choices for non-linearities and good ways to initialize, and things like that. Okay, so we'll see these considerations here and there. Maybe towards the end of the next lecture, or the lecture after that, we'll talk about these weight initialization aspects and so on. Okay, I want to start talking about convolutional neural network, but I thought it should be a good use. I mean, so we'll probably not cover much of it today, maybe just the basics. I thought it would be good use of time to also talk about, since we're talking about backpropagation, and I mentioned PyTorch a couple of times, you'll see that PyTorch is what we'll use, or at least suggested to use in most of the assignments, in assignments 2, 3, and 4. So at least the example course use that. So I thought it would be good to see how PyTorch does your backprop. Okay, so that's a code that we can get from the link in the lecture goals. There's a link there, so it links to this particular repository by this author. And I'm just looking at one of the notebooks. The notebook is linear regression notebook. Okay, and that's what I've opened in Colab. Okay, so I want to just focus on the backpropagation part and not really all these imports. And you'll see these imports, by the way. It's not. So whatever we've covered so far till now, okay, without convolutional neural network part, is useful for your first assignment. PyTorch stuff that we're discussing now, and CNNs that we'll discuss right after this, they're mostly useful for your second assignment. Okay. So if you want to get started on first assignment, you can get started soon. So let's look at this PyTorch example through the lens of doing linear regression. Okay. So there's a bunch of imports. Let's not worry about imports for now. Imports, this is how you'd import the torch package itself and some additional functionality in there. Device, again, so this is where you can see if you can get a GPU, or do you want to work with a CPU. Okay, if you want to work with CPU, you don't really need Colab unless you're collaborating. It's if you want to share code and so on. But otherwise, you can try to see if you can get a GPU or a TPU. A TPU is a Google-specific hardware, which also does, which also is helpful for training deep learning models efficiently. Because these are just computational speed ups, but actually very important. I should not use the word just. They're actually very useful, especially in assignment 2, when you do some training in CPU versus some training in GPU. GPU is much faster. So you can change it and
so what's the difference between the TPU and the
TPU is just Google proprietary technology. It's just tensor processing unit and graphics processing unit, I guess. So GPU, for example, the leading manufacturers are AMD and NVIDIA. TPU is very specific to Google. I think you can only pick them on Google Cloud, I think. Yeah, I may be off here, so if somebody knows this, then please add in. Yeah, so they both are hardware accelerators. Okay, they're just better than CPU for training deep learning models. But you won't find TPU elsewhere except for Google, I guess, properties for now. Let me not do that. Let's pick CPU itself. And some additional imports, matplotlib, pprint is prediprint. And NumPy. So okay, let's focus on, these were the same imports we did earlier. Okay, so now let's create a synthetic data set. Okay, so instead of that specific spiral data set that we use, this is one other way to create a very simple synthetic data set. Okay, scikit-learn is a package which some of you might have used for 575 or 572. It has a function called make regression. Okay, and so if you say, hey, how many features do you want and how many samples you want, it actually creates a regression example. So here we're switching context from classification to regression. So, but that's fine. Just a different supervised learning example. So make regression, you can, creates a data set. Okay, here, since we said number of features is 1, we can actually plot y versus x. It's just x versus y. Here is this scatter plot of x versus y, and you want to fit a line ideally. Okay, so you can, it's just simple regression situation. Right? Let's run it. And so this is the data set we have. Now, what we're going to do is create. So x and y here, when we said when you said make regression, x and y happen to be numpy arrays. Okay, so actually let's check it. So type of x, you can see it's a numpy n-dimensional array. So in fact, x dot shape should give you 100 cross 1, 100 examples, and 1 is the number of features. Right. So similarly, type of y is a numpy nd array. Okay. Now what we're doing in the next step is actually just make them what I call tensors. Okay. Torch, what it does is makes, provides data structures which are very similar to numpy nd arrays, but they have one extra feature, which is that you can deal with gradients. Okay. You can deal with computing local gradients. Okay. That's what we want. Right. So this is just type conversion. So start from x and create a slightly different x, which is a torch tensor. So it's almost the same. So if you ignore deep learning or even gradient descent stuff, you can use x and this torch tensor and numpy nd array kind of interchangeably. They have this almost same basic. You can use them interchangeably. Like wherever you're doing x plus y, you can, whether it's a torch tensor or whether it's numpy.nd array, it doesn't matter. Okay, here's a small piece of code. What is it doing is it's defining a class, but we actually are not, it's not super important. So you will see this type of structure in assignment 2 onwards. But here I just want to show you a simple class. It's a linear regression class from which we can, if we instantiate an object, that object, when instantiated, you have to define the input dimension. Let's say input is 1 dimension. Then it just sets it sets what is this parameter. Remember, for 1D model, you just need to have a slope. Okay, you can actually also add a intercept, but let's say it's just a slope. Are we doing the slope here? Yeah, sorry. So it's just slope. Okay, for simplicity, we're not even considering intercept. And then we are defining a forward function, which is just, by the way, don't be confused about this. It's just when you instantiate the class and you pass an input, it's just going to call the, what's it called? X times the slope. Okay, so actually we can, X times slope. Okay, so what is the linear model, right? So if you give an input x is 1 dimension, I just want to multiply it with some coefficient, the linear model coefficient, and then just that's my output. I'm dropping the intercept. Intercept is 0. Okay, and that's being shown in this way only because that's the way PyTorch typically PyTorch deep learning models are also defined that way. So let's not worry about this complexity here. It's just doing some coefficient times input. Okay, now what we're doing here is defining the model, instantiating the class with an object from the class, defining the loss function, okay, and defining the loss function. So creating the loss function, and we'll compute the loss in a second. And then we're also defining what is called an optimizer. SGD is exactly the GD part corresponds to gradient descent. Okay, so S stands for stochastic. We'll talk about it intermittently. It's not the focus of this course. There are many other options, but this is the one which lets you do, old values is equal, new values is equal to old values minus some learning rate times gradient, right? So the learning rate parameter, for example, is this. And what do you need to gradient descent over? is the model parameters. So that's how you define these. And then I'm also sending these to device. So this makes sense when, if you have torch tensors, if you want to send them to GPU, so that GPU has, by the way, it has its own RAM. So if your data lies in the regular computer RAM, you want to send it to the GPU RAM, okay, or the video RAM. So that's how this is how you do it with a .2 function call. Okay. Again, these are some details of PyTorch. Let's create the class and let's create these model loss function optimizer. Okay, so now here is the interesting step, which is the backdrop step that I want to focus on. So what we're going to do is make all the gradients, local gradients 0. Okay, all the gradients 0. Set the model in the train mode, which just means, hey, start computing gradients every time we do a forward pass in the computation. Okay, every time we do a forward pass, train mode just makes it remember the gradients, okay, of the parameters. And here's the forward pass for the given parameter. So the model object has the current set of current parameters. Here is just a slope. So given the input data, given the training data, use the model to produce predicted outputs. Predicted outputs are y underscore. Okay, you compare y underscore with the true ground truth, output values. That comparison leads to a loss scalar value. Now this loss, is the output, final output of your computational graph, right here. Then you do loss.backward. We'll compute all the gradients. Okay, so sorry, we'll compute the gradient of the model of the loss with respect to the model parameters. Okay, here the model parameters are slow. And then optimizer.step does exactly that gradient is instead. New parameter is old parameter minus learning rate times this gradient. Okay, and then you can evaluate what the predicted predictions are, and we're just plotting those predictions. Okay, so what we want is actually just let me run this once. Okay, so you can see the blue, the orange are the original data. Okay, so it's exactly the same as this data. It's just in orange, and the blues are my predictions. Okay, are my predictions after doing one step of my gradient descent. So why is it one step? Because I said, hey, set everything to 0, make predictions, compute the loss, compute the gradient, do the gradient update. That's what's happening in this cell. There's no extra for loop like in the previous example. So it's just doing one step of gradient descent. And then we're just saying, hey, with that, after that one step, what is the new predictions? And then just let's plot the predictions. That's what we're doing here. So right now, the predictions are like this, which means that we didn't get the right slope. Okay, so if you run the cell again, you can see now the slightly improved. Okay, and so let me run it a couple of times. Sorry, not the next one. I ran a couple of, now you can see that the slope is now closer and closer to this data. So ideally, what should the blue line be? The blue line should really cut through this orange dots, right? That orientation. So you can see. Okay, so now you can see the line is fitting better to the data, right? So that's like really bare bones PyTorch for you. So behind the scenes, these are the 2 steps that we saw in the previous lecture and up to now that are happening. Okay, I strongly encourage you to try out that repository. I know the code is a little bit old. It says PyTorch 1.7, but it may be, since it's at least that notebook is kind of relatively simple, it might work with newer versions of PyTorch as well. So any questions about this part? I mean, this is just to get you prepped up for assignment 2, which is a little bit later. But if you want to get started on trying out PyTorch, not just this website, but PyTorch's official website also has really nice examples, and we'll look at a couple in maybe next lecture of a CNN example actually. But wanted to give this example right now so that if you want to get familiarized yourself with this, then this is a good point to also start. Okay, so any questions? Okay, so let's actually talk about a different architecture. I mean, of course, we're we didn't spend too much time on feedforward neural networks, so, but we will revisit them and then try to contrast with feedforward neural networks, how convolutional neural networks are different. Okay, I'm omitting the word model, but it's a CNN model. Okay. Okay. So CNNs are very similar to feedforward neural networks. Okay. And each node, whether in the node, the hidden layers nodes especially are called neurons. Okay, and that's why it's a neural network. It has its own history because of which, I'm trying to, because of which that such a name, is being used. So each neuron is generally associated with a bunch of weights and a bias, and we'll see that in the next couple of slides. Okay, and we'll see that why that is the case even for the feedforward network. I didn't explicitly point it out, but I'll point it out in the next slide. How each node in the hidden layer is associated with a bunch of weights and a bias. Okay? A bias means just think of as a scalar. Okay, and bias is just going to be one coordinate of the B vector. What does a node do? It's a computational, it's a node. Think of in a computational graph. What does a node do? It gets some input. It's going to do some dot product of vectors, and it applies nonlinearity, like max of 0, x. And we'll see this in the next slide. How this, what does node do? Okay, and the new convolutional neural network as a teaser is going to be very similar to this. The nodes are going to be exactly the same, at least in terms of like the operations, they're going to do exactly the same operation. The new thing is going to be that they're just going to kind of not have too many parameters. Okay, CNN is just going to reduce the parameters by exploiting something about the type of data set it works with. CNNs are generally used with images, and images have some structure, and we're going to talk about the, what natural properties images have, and because of which, although the nodes are almost doing the same operation, which is like dot product of vectors, we'll see that the number of parameters overall in that model can reduce quite a bit. Okay, and we'll see that after we discuss this, what does node do, right? So in a feedforward network, right, given an input x, okay, yeah, let's not put I here. So given a vector x, we eventually transform it to a score, right? Like scores for each of the class. Now, let's say at the beginning, the first layer, let's say that we only have one hidden layer, then you have, let's say, n inputs. Okay, so let's say the number of features is n. Let's say if you want to think of 3, then 3. What you do is that you think of this. What I'm trying to show is that x1 to xn is the input, and then everything else happening after it produces one output, which is here using the notation O. Okay, O subscript j. So remember, in our example, there were 4, let's say, let me drop all these. So focus on the first neuron. Okay, so first neuron is taking all these inputs. Let's say there are 7 inputs here, all these inputs, and is producing one number as an output, right? So there's only one number, one edge going out, and there are all these 7 inputs coming in, right? So that's exactly what this is. So the 7 inputs coming in and one number going out. But along with the 7 numbers, there's also those weights. Okay, there are going to be 7 weights that will be multiplied. Okay, that will be also input to the neuron. Okay, in the sense that how do we see that here? So these are the 7 inputs, x1 to x1, x2, and all these guys. In addition, that the weights correspond to the first row of a W matrix. Right. So if you remember here, if I have an input, let's say 2-dimension 1 and 2, I'm going to also use the two rows in the first, the 2 weights in the first row of the W matrix. Yeah, 2 rows, 2 entries in the first row of the W matrix. Those are the weights. Okay, these 2 weights and these 2, these 2 numbers and these 2 numbers and the first number together will be used to compute the output of a neuron. Okay, let's see. So these weights are just the first row of the W matrix. So similarly, if it was a second neuron, let's say if you want to produce a second output, then it's going to be the same inputs, but the second row of the W matrix, and so on. So what do? We take the row, multiply element wise, sum it up. That's the summation operation, and then we apply then we also give a non-linearity. Okay, so we add a non-linearity, which is that one coordinate of the B vector, and then apply the activation function, which is like max of 0, x or sigmoid or something, and then we produce the output. Okay. That's actually really in detail, like what's happening inside a hidden node. Okay, if you step out, we know what is happening, which is just matrix vector multiplication plus a bias vector and then some nonlinearity. But that's at the vector level. We are in this picture, we are just looking at the single coordinate output of each hidden node. Okay, and that's elaborated this way. Yeah, so as I said, for example, in the 3 input case, and let's say let's focus on the last one for simplicity, for a slight change. So let's focus on the last one. So the 3 inputs are come in here. There's going to be 3 weights. Okay, 3 weights and 3 inputs together. They'll be multiplied, like x1 times the weight and x2 times the weight and x3 times another weight. And then a bias will be added, or the third coordinate of the B vector will be added, and nonlinearity will be applied, and then that number will be fed forward to the output. Okay, so that's what's going on in this picture. So that's just feed forward. Okay, we are not yet going to define the convolutional neural network architecture yet. Okay, so now let's talk about some structure. Now we're going to change this layered view. So in the feedforward neural network class, everything is a layer, right? So input is a layer with nodes one below the other. Hidden layer is also a bunch of nodes, or neurons one below the other. Similarly, output is a layer with nodes one below the other. So whether you had one hidden node or let's say 10 hidden nodes, let's say here, for example, if we had more hidden nodes, it's just a layered view. Okay, each block here kind of corresponds to a node as a neuron. Okay, that's all these are. Okay, we're gonna kind of move away from that. Okay? And why is that? Because now we're gonna start talking about that data set. Okay? So far with feedforward neural networks, our input was like a feature vector. So even here, it's a feature vector. It's a 7-dimensional feature vector, or you can think of the original raw features as 2-dimensional, right? Instead of that, now we start thinking of input as a tensor. Okay, so what is a tensor? A tensor is nothing but an n-dimensional array. So in particular, this is the data set that you'll use in assignment 2, but it's a data set of images. Okay, and each image has a class associated with it. In fact, it's a 10 class, and that's why it's a 10 in the suffix there. And so each image is a 32 times 32 times 3 container, and we discussed about this data set, this type of data point representation briefly in lecture 1, right? So this has 32 rows. Each image, okay, each little image here, there are many images being shown here in this slide. Let's take the top right image. That image has 32 rows, 32 columns, and 3 slices of such matrix. Okay, so it actually has 3 matrices. Why 3? Because each matrix kind of corresponds to one primary color. Okay, so let's think of it as like RGB. Okay, so if you think of this image as my data set, so this 32 cross 32 cross 3 as my input, and my output is like this 10 classes. How do I deal with this input, right? You can think of that as like you can vectorize it. So although these are arranged in a 32 times 32 times 3 type of a object, which is a tensor or a 3-dimensional array, you can vectorize it, right? You can, hey, first row followed by the second row number should be, appended, and the third row number should be appended, and so on. You can make a really long vector. Okay, if you do it that way, then you can imagine how many connections each neuron in a feedforward network will have to have, right? So if you just think of it this way, right? So 32 times 32 times 3, if you just vectorize it, it's a huge number, right? And from each of those 32 times 32 times 3, need to go to each neuron in if the next layer is a feedforward neural layer, if it's a feedforward layer. Okay, and so that leads to a massive increase in the number of parameters. So just one neuron needs to be associated with 900 or 1,000 parameters, right? And the second neuron will be another 1,000 parameters. Third neuron will be another 1,000 parameters, and that's just because you're looking at a input and image. And now you can imagine if 32 cross 32 cross 3 is a really small image. Okay, typically if you snap photographs on an Android device or an iPhone device, you at least at the minimum will have a huge, I mean, at least a 1 megapixel image. Okay, so a million coordinates if it really vectorize it. Okay, and in fact here it's 3 million even for a 1 megapixel image. So just too many parameters for associated with each neuron. Okay, and so this is something that kind of tells us that maybe the first layer of the first whatever processing step that we do when we get an input when we get image as an input, hopefully is not a linear layer, because if it's a linear layer, each neuron there is connected to every kind of pixel or cell of a input image, then it's going to blow up. Okay, number of parameters. Okay, so we'll still take the CNN still conforms to the layer point of view, but now the layers are going to be not just one neuron below the other. We're going to have something richer. Okay, and that richer idea is that each layer will now have a width and depth, in the sense that each layer now, in this layered point of view of defining a model, will now not just be thinking of neurons and nodes one below the other in like a linear sequence, but these neurons are arranged like a three-dimensional array. So each layer can be visualized as like a box, basically as a tensor. And so each layer will have a width and depth in addition to height. So if you think of the feedforward layer here, you can just think of this arrangement of neurons like a height of the neuron, height of the layer, right? In addition to height, we'll have width and depth for each layer. Okay, in defining that. Yeah, so there is the slight difference between, so the layer will have a depth by itself, and the neural network itself will have a depth. Okay, so if you remember this was a one hidden layer neural network or a two layer neural network. Okay, so that's the depth of the neural network itself. What we're going to talk about is the depth of each layer in a CNN. So there's a layer depth and the network or the model depth. Okay, there are two different things. Just wanted to disambiguate that here. So let's talk about how we can do that, right? So let's start building our intuition towards that. So on the left side is the usual, is the picture we've been seeing throughout. If you want to, so let's take one step at a time. So what we can do is, hey, you have an input that was originally an image, right? So instead of even vectorizing that, let's think of that image as like it's a three-dimensional array. It can be visualized as a box, right? It'll have its own depth being like three R, for one for red, one for green, one for blue, RGB, and then 32 cross 32 as width and height, right? And then what we can do with the hidden layer is that, let's say we had we have 4 in the left figure, but let's say we had 64 neurons. Okay? Then what we can do is we can arrange it as a 8 cross 8 box, right? 8 cross 8 matrix, right? So we can arrange these neurons, computational nodes, spatially as 8 cross 8 box. Okay, so that's how you get a. Although we had the neurons one below the other, we can arrange them like a box. Okay, so the first neuron, second neuron, third neuron, fourth neuron, and so on. Okay, like a box. And similarly, the output we can again make it as a box. Of course, there's no width and height. Like width will be 1, height will be 1, and depth will be like number of classes. Okay. So what we've done is not really changed much. Input is rearranged into a matrix. Like every time you have vector, bunch of numbers, you can always reshape it into a matrix, right? In fact, NumPy has a reshape operation that you can try out to reshape a vector into a matrix, for example, or a matrix into a different size matrix. So that's what we're doing here. So at least for getting width and height, it's not a big deal. I mean, you're just rearranging spatially neurons in a different way. And this green bar here just shows, hey, if you pick a neuron, that neuron is connected to all the inputs, all the outputs from the previous layer, or all the inputs. Okay, so that's what this green bars are illustrating. If you pick any neuron, that will connect to everything in the front. The reason I'm highlighting this is we'll see how CNN's layer will have certain changes from this. Okay, so far what we've done is nothing, right? So from left side to right side, there's just a rearrangement of the neurons, a rearrangement of the nodes. Any questions here? Okay, so now we're kind of deviating from feedforward neural network. So far, nothing changed. Some rearrangement, spatial rearrangement of these nodes. Now we're gonna do a spatial rearrangement, which still seems like it's not a big change, but now that that layer point of view gives us slightly different computation going on. Okay, at the layer level, which is that this rearrangement of neurons, we're gonna actually have depth. So how are we gonna have depth? So which means that neurons are in front of each other or behind each other, behind the others. Okay, so there are some neurons which have neurons behind them, some neurons which have neurons in front of them. That's why we get depth. Okay, so that's all it is. So this box here on the left, on the right side, has depth, whereas the box on the left side just had width and height. Okay, so if you think of, so it was a depth of 1 on the left side, and now that is depth of, let's say, 3 on the right side. Okay, so we are going to rearrange the neurons. It's still, so this box, think of it as like circles, bunch of circles arranged nicely. Okay, one behind the other, one below the other, and so on. Okay, so what is this box? What does this box constitute, right? So this the box on the right side, and we'll try to understand it at the level of input to the first transformation, the first con layer transformation. Okay, so input has, as I said in this running example, is 32 times 32 times 3, and finally, after the model has to spit out 10 scores for 10 classes, right? So previously we had something like this. Here I just added one more hidden layer. We said, okay, if you have 2 hidden layers, then you can just rearrange it this way. But what we're going to do is, now if we had something like something equivalent to that, would be, now we had an input which is 32 cross 32 cross 3, which is already a tensor. It will be processed to another box which has depth. It will be processed to another box which still has depth. Then it will be, finally we get to a score vector which has depth but no height and width, in the sense that height is 1, width is 1. So you can see that green bar to the right side, and this pink box. It's also a box to the left side which has depth of 3. So think of this depth is 3. Here the depth is 10. In between there are 2 other boxes. Okay, and there, and if you look at the second box, it's showing the neuron arrangement. So there's some neuron at the top left, there's some neuron next to it, some neuron next to it. Similarly, there are 2 neurons right next to each other. There's a bunch of like 5 neurons, one behind each other, and so on. Okay, so we're going to arrange neurons like that, and remember, each neuron outputs 1 number. So since each neuron outputs 1 number, whether it's a feedforward neural network case or here, if you collect all those numbers and arrange it this way, it's again still a tensor, right? So the tensor will have some depth, width, and height. Okay. Okay. So yeah. So we'll focus on this. How do we get this cuboid or box structure, and what does it mean? Like, why are we arranging this? So far, so whether we do this box structure arrangement of neurons, or whether we keep them vertically one below the other, as long as they're connected to everything in the previous layer or everything in the input, there's there's nothing that we've gained. Okay, but we'll see what we gain by doing rearranging neurons like this. In particular, that's going to be what we're going to discuss is the con layer. I will not talk about, so fully connected layer is the fully connected layer is the same as the feedforward hidden layer. So we'll probably not spend much time on it. There's one more auxiliary layer that's going to be useful for us. We'll talk about that when we get there. It's probably, we will not talk about it today. We'll talk about it next week. Okay, but our focus is mostly just on the con layer. So I want to although we are focusing on con layer, so how does the overall model itself look like? So here's an example, just to give like one more step away and say, hey, we know feedforward networks are exactly, you just need to define how many hidden layers and how many nodes in each layer. Similarly, for a con layer, a typical architecture may look like this in a really small architecture, but input to a con layer, followed by a pole layer, followed by a fully connected layer, which is like the hidden layer of feedforward neural network, and then the output. Okay. Now, we'll spend some time on con layer. It looks like we're running out of time, but we'll try to spend some time on con layer today and maybe early next class. But what does con layer do? It takes a the neurons themselves compute exactly like what feedforward neural networks do, but Con layer takes a tensor as an input and produces a different shaped tensor or a different shaped this three-dimensional array as an output. Okay, and pool layer again takes a tensor as an input and produces tensor as an output. But there's some minor changes it does. It just reduces the height and width by half. Okay, and we'll talk about this later. This is just a teaser here to say what does that layer do. A fully connected layer is exactly what is exactly like the hidden layer of a feed-forward neural network. So if it has an input which is a tensor, ignore the tensor structure, just vectorize it. Basically, keep all the outputs one below the other, make it a vector, and then hey, you have a vector. How do you pass it through a hidden layer? Pass it through a hidden layer. You have vector matrix multiplication and produce some output, right? And the number of hidden units you choose there determines what is the dimensionality of the output. So, I mean, if you think in terms of layered view, I'm just trying to spend some time on the layered view because it doesn't change much from the feedforward layered view. So there's some input. In the feedforward case, there will be hidden layer 1, hidden layer 2, hidden layer 3, let's say. Here it will be input, con layer, pool, let's say, if you want to use pool. You can also use, again, another con, let's say another pool, a fully connected layer, and so on. This is how you still retain the layer view. Okay, so but actually let's focus on the con layer. I want to leave this class with at least introducing why we arrange neurons next to each other like a box. Okay, for that I want to introduce the notion of a filter. Okay, so what is a filter? Filter is a collection of weights. Okay, the bare bones definition of filter is just a collection of weights. You can also think of that as a linear function. Okay, it's a collection of weights, but those weights are arranged again like a box. Okay, so it's a parameterized by a tensor, like the number of weights, for example, for a filter could be 3 times 3 times 3, which means that the number of parameters of the filter is 27, and that's just one filter. Okay, so filter also looks like a box, and so a con layer's parameters can be thought of as a collection of these filters, or the collection of these filters weights. Okay, so if I have 10 filters, then I'll have 10 such boxes, and all the weights in those related to those filters are exactly the weights of this con layer. Okay, so how does this filter how do this collection of filters, let's say 10 filters, produce an output tensor given an input tensor? Okay, that's what we'll talk about now. We are going to convolve this filter with the input tensor across width and height to produce one matrix, one slice of the output tensor. So let me illustrate what I'm trying to say here. Actually, let's use this link because it's kind of easier to understand, at least at one layer level. So yeah, so think of left-hand side as an input. Okay, input tensor. It doesn't have depth because it's a grayscale image, so nothing much is going on. So the red boxes that you see is an example of one filter. Okay, so what is that filter that we're going to? What is that filter? It's actually this is the filter. Okay, 0. So the filter doesn't have. In this case, the filter has depth of 1, width of 3, and height of 3. Okay, width of 3 and height of 3. So that's why there are 9 numbers. Since depth is 1, the number of total numbers is 9. Okay. What does filter do? So there are 10 filters, let's say, in the con layer. We're only looking at one filter. Okay, what does one filter do? The one filter, what it does is it's a bunch of 9 numbers. It's going to go from left to right of the input tensor. Okay, so on the left to right, and then again scroll one step below, left to right, and so on, and produce one output. So remember, when I'm on the left figure, when I'm at the top left, there's one cell that is highlighted on the right side. Okay, that's the output of this filter. Similarly, if I move one step to the left, there's one more output. Similarly, one step to the left, there's one more output, and so on. Right. So I'm producing one number on the output by using this filter on the input. Okay. And so we do that sliding operation from left to right top to bottom, and we can produce this output slice. Okay, so that output slice is shown on the right hand side. Okay, that's what a filter does. So if I have 10 filters, I'll get 10 such slices. I'll put those slices together, one on top of the other, and that's my output tensor. So if I have 10 filters, I'll have a output tensor of depth 10, because I have gotten 10 matrices and 10 output slices, and I can stack them one on top of each other. Okay. Any questions here? Okay, it will become more clearer once I again mention a couple of more things. So filters are basically, just think of it as small boxes, like exactly what's happening in that picture. This red box on the left figure is like a filter. It doesn't have depth in this illustration because the image is not RGB, not a color image, so it's a black and white image, so it doesn't have any depth. Okay, so if the filter is like 3 times 3 times, so if the input is has some depth, let's say if it's actually input is a color image, then the depth will be 3, 3 channels for the 3 color channels. Then the filter will need to have the same depth. Okay, the filter depth should be the same as the input depth. Okay, or if the conv layer is somewhere else, then the filter should have the same depth as its input tensor. Okay, then when we slide the filter, what we get is what is called a 2D activation map. So when we are sliding this filter from left to right, and then again scroll down left to right, scroll down left to right, and so on, what we're producing on the right hand side is called a 2D activation map. Okay, it's called a 2D activation map. And we will, I think I was mentioning earlier that these 2D activation maps, the number of maps depend on the number of filters that we're going to define, and the parameters of the filter. Here the parameters of the filter are fixed. It's exactly like 0, -1, 0, and so on. These are called the parameters of the filter. These are the parameters that we have to find, do gradient descent over, in the sense that we'll have to find the gradient of the loss with respect to these parameters, and then do updating of these parameters. Okay. Okay. So yeah, I think going from filters to neurons will take more time than 5 minutes. So I'm gonna just spend some more time on filters. Like, is the idea of filters clear, and what filter is trying to do? I mean, not the neuron level. Don't worry about the neuron. So let's come back to this picture, right? So we have some input like this pink box. Okay, let's say we want to create this blue box, right? How do we get to this blue box? All I'm saying is, let's say this blue box has some depth. Let's say a depth of 3. Okay, how do we get this depth of 3? Depth of 3 just means there's like 3 matrices, one stacked next to each other, like, right? So each matrix, you know that matrix has a height and width, right? So matrix is literally like a 2D plane, a square, right? So if you stack 3 matrices next to each other, it's a tensor with depth 3. Okay, why, I was trying to explain that if you have some input, let's say the input itself, like some tensor, okay, if you have 3 filters, each filter is responsible for creating one of these slices. Okay, one slice is produced by one filter. So if you have 3 filters, you get 3 slices. And how does each filter produce a slice? It's exactly like this. So it's gonna go from left to right. And if here the filter happens to be a 3x3 filter, so that's why the output slice is almost the same size in terms of width and height as the input slice. But we'll talk about how that output tensor size can be different later on. Okay, so each filter just runs from left to right on the input tensor and then produces a slice at the output. Okay, so any questions about how you can get a tensor from a tensor? We'll get to neurons next class, but I wanted to at least talk about how you get a tensor from a tensor. Any questions, or where did I lose you guys? I think at least that much. If you can tell me, then I can, if it's short, I can repeat it now, or we can again take it up. We will take it up. Okay, I'll repeat some of these next class.
Professor, Can you please also talk about slide 59, those numbers?
Oh, 59 here.
Yes.
Okay. So here I was just showing to, so what I was showing here is exactly the same as before. So think of the greens, think of that there is these greens are exactly these numbers here. So although you don't see the numbers, so the greens are supposed to be like the intensity at that pixel. Okay, so intensity of 1, intensity of 1, intensity of 1, and so on. So just think of these greens, including, so all the big numbers, the big bold numbers are the input. Okay, input is supposed to be tensor, although here you're only seeing a matrix, right? So it's a matrix of size what, 5 cross 5, right? Here you're only seeing a matrix because you can think of depth to be 1 in this example. Okay, so these numbers here are the input. Now the sliding operation that I was talking about is exactly, so think of a 3 cross 3 filter. Let's say the filter weights are in red. Okay, so this red, 1, 0, 1, 0, 1, 0, 1, 0, 1 is the filter weights. To produce the output tensor, is one slice, or basically the 2D activation map. What do you need to do? You need to slide the filter from left hand to right hand side and do element wise multiplication and add them up. So these numbers, red numbers, are getting multiplied element wise, which is like 1 is getting multiplied 1, 1 with 1, 0 with 0, and so on. So these red numbers are getting multiplied with these numbers and then getting added up, and that addition is 4, and that's the first entry of your output slice, 2D activation slice. Now what I can do is move to one step to the right, then I'll be multiplying these red numbers with these set of 3 cross 3 numbers. Okay, that multiplication and and summing up the result will give me the second number here. Okay, similarly, like I'll move one more step to the right after that, multiply element wise and add them up, and that will be the third number. And that's how I'm going to create the output slice. Each filter, if it creates such a matrix, then you can stack those matrices together, and that's your output tensor. Does it help? Let's actually, I mean, so I'll repeat this again next lecture. But if it wasn't clarified, for those of you, please stay back and I can explain it again. We can do this some more time so that it's a little bit more clear. But I'll explain it for if you're running out of time in the next lecture. Also, I'll be talking about Conv layer again. So we'll revisit this. So for interest of time, I'm gonna just pause the recording so folks, end the recording so folks can leave.